efficiency.
Yeah, I'm amazed you guys is still here. This is almost the end, and don't worry about the title. I should change the title to randomized algorithms, but I didn't. But yeah, I need to look at the slides because I already forget what is inside. Oh yeah, this week we learned a lot about how to solve least square problem using a lot of randomization technique. And for example, one way to do is you have a matrix, you multiply left or right or on top or from down some matrix, random matrix. The other way is you have a lot of term, then you just each step you sample one term and do something. And or maybe we also have from some talk, instead of sampling a term, you can sample one coordinate or a subspace. There is many randomization technique. And today we will talk about a slightly more general problem. Generalized linear model. You can think it's like you replace the square term by some convex function f. And technically we can deal with each term have different function, but for this talk you can think it's just the same function. But one special thing about this talk is we almost are not going to assume anything about fi. It can be non-smooth. For example, one particular example is imagine your fi is let's say 0 for positive number and infinity for negative number. Then that is linear program. And so for many applications, sometimes fi is non-smooth. And we want to show how to use randomization technique to solve generalized linear model. And why this is difficult. For example, for linear programs, if you have a point of how, and with many constraints, and you want to approximate by another point of how many constraints you need, imagine the origin body is a sphere, how many faces you need to approximate a sphere, then in general, you take exponential in D. But in general, especially if the fi is smooth, you can just run SGD will work. But one problem for us, theoretical computer science people, is the converging is just 1 over epsilon to some power, usually is epsilon 2 square. And in this talk, we will focus on getting a log 1 over epsilon convergence despite using randomization method. And just for background, what type of one time we care about, we want the algorithm is asymptotically fast, namely they are slow, namely it work for very large n. We want the running time is weak. In TCS weekly mean the convergence rate is log 1 over epsilon, and polynomial time mean your running time cannot depends on polynomial, depends on something like condition number. We want the running time always polynomial as long as the input is polynomial size. So this kind of restrict what kind of algorithm you can use, and yet we will show randomization is useful even for those strict requirements. Just as an example, for least square problem, what type of algorithm satisfy all of those requirements? Turns out you can solve least square in this running time. Zero number of A means the number of non-zero in A. So 10 or yeah, roughly 10 years ago, they show you can solve least square problem in linear time linear to the number of non-zero plus d to 2.38 times some log 1 for epsilon. And roughly speaking, what they do is they just multiply your matrix A by some special random matrix such that it preserves the sparsity. And here we will use O tilted to hide any log term, but the O term only hide the constant, some very giant constant, but it cannot hide dependence on condition number or something else. It can only hide constant. And notice this running time is very nice in the sense to solve least square form. If you want to solve to machine accuracy, you need to read every entries of the matrix. Otherwise, changing one entries can change your solution. So you need to read the input. And randomization technique can only take you to a certain pace. You can make a tall matrix become square. You still need to solve a square matrix. So you still need to solve a D by D matrix that currently the best is D to something. So this running time is amazing in the sense by reading the matrix, you can reduce to a D by D matrix, and then you can do the best you can, you know. In fact, this is a general reduction. If you don't like this type of running time, there's different type of running time you can do. But you can think they show how to reduce the tall matrix to a square matrix in a very generic way that preserve a lot of property. And today we will discuss generalized linear model. We don't get such a tight running time. What we get is a running time like this. We cannot just read the matrix once. You can think this running time is like this. This is the sparsity of A. This ND is like when the matrix is dense. We don't get to the best. We just halfway there. We get square root of sparsity times the dense case plus D to 2.5. This is also not the best. For linear programs, the current best running time is exactly same as solving linear system. So the best is 2.38, and we only get 2.5. And so this is roughly what we will discuss. Any question about the setting? Yeah, I don't have too much slides. Yeah, you see the offer is there. There's many people. And notice when the matrix is tall and dense, tall means n much larger than d, then our running time is linear, namely our running time is nd if n large enough and a is dense. So this is already pretty nice. And roughly speaking, what we do is we combine some laziness with randomization. You can think randomization is kind of a laziness. You don't want to read everything, you do something to be lazy, and usually to be lazy, you do need to do it randomly. Otherwise, someone will notice you. Yeah, so you can think this is a guide to procrastination. I'm expert on this. And turns out to procrastinate, what you need is you want your algo to be robust. Otherwise, if you randomly do something stupid and your algo is not robust, then it will fail. So roughly speaking, what I want to discuss is how designing robust algorithm can lead to an efficient algo. And here, just as an example, let's say we have an iterative method. Each step, you compute some vector function g, and then you use the g to move your current point x. And sometimes we have some noise in the input or output of the vector g. And what we want is we want the algorithm robust under noise. You have some noise input, output noise. We say an algo is robust to certain noise if it doesn't affect the convergence rate. But where does the noise come from? The noise is not come from user. Instead, the noise is come from our laziness. Sometimes each step involves too much calculation and we want to be lazy. We forget about some term. Then it creates some noise or error. And essentially what we show is we discuss how robust is the intuple method, and we show almost all calculation can be skipped. And one important thing is usually when we talk about noise, we talk about unbiased noise. But because our noise is come from our laziness, sometimes we skip some calculation that is not unbiased. So we lead our algorithm robust to a biased noise. Just for a very classical example, one algo that is very robust is the gradient descent. Gradient descent is just this. You look at your current gradient and you go to the negative direction. And gradient descent is very robust under L2 noise. For example, if you add a noise after the gradient, as long as the noise epsilon is unbiased and have some bounded L2 norm, then it converges for certain class of function as fast as without noise. Did I see someone ask a question? Okay. And this is very useful property. For example, if your function involves a lot of terms, then you can sample one term, use that to construct an unbiased estimator. And then that will give you the stochastic gradient descent. Or if you have a lot of coordinate, you can sample one coordinate, use that direction derivative to get the unbiased estimate of the gradient. Then you will get the coordinate descent. And this robustness of gradient descent is super useful. In the talk today, we will discuss the robustness of Newton method. Usually when we talk about Newton method, it is very not robust. You probably see some picture about some fractal. If you start at different point, then the convergence behave very differently. Yeah, Newton method is this. You just every step you look at your quadratic approximation of your function and you minimize that quadratic function. And but turns out you can make some assumption to make sure Newton method always converge. This is the standard theory by Leshoff and Nimorsky. Roughly speaking, you can think the condition is as long as the first derivative is bounded by second derivative to certain power, the Newton method converge. And what the nice thing is they show any convex function can be approximated by a sequence of self-concordance function. So it is kind of without loss of generality. If you want to minimize some convex function, you can use the reduction to reduce to a sequence of self-concordance function. And each step you just do one step of Newton method and switch to the next method like a homotopy method. And this will guarantee convergence in polynomial time. But in this talk, we will not really use this. We will just discuss how to use randomization to be lazy. So, and in this talk, we will focus on generalized linear models. So our F always of this form, sum of a bunch of Fi. And what we will discuss is turns out if you use the reduction, you can always make sure Fi is self-concordance. And when Fi is self-concordance, turns out Newton method is robust under certain L infinity laws. I will be more precise in next slide or so. And what we'll mainly discuss is how we use this fact to get a very surprising one-time improvement. Yeah, just to highlight, this is a non-trivial problem. For linear program, people have been studying for decades or centuries. And in fact, for linear system, we probably know a few thousand years. I don't know when people notice you can solve it in n cube, but we know how to solve linear system in n to some power for a very long time. But for linear programs, it is a different situation. We only know how to solve linear program in polynomial time in 1979. And another thing is linear programs is a special case of linear is a if you can solve linear programs, you can solve linear system because the constraint involve AX equals to B. So you should imagine in this part, this is the running time on different year, the exponent on the running time. You can see both running time is improving. And there is always a gap because if you can solve linear programs, you can solve linear system. And there is always some gap. And the gap is only closed a few years ago using this robust integral method. And in fact, as a theoretician, you can continue asking, can we do better? For example, if someone tell you how to solve linear system in quadratic time, can you solve linear program faster? And currently, we know how to solve linear program in n to 2 plus 1 over 18. So we're still not getting there, but at least for the current regime, we are already getting the match result between linear program and linear system. And in this talk, we'll focus on the tall case because this is a randomized conference, so I need to have some randomization technique here. Yeah, anyway, so now I will explain a little bit more about the robust IPM. So again, the setting is a generalized linear model. N is the number of terms, and D is the number of variables. And you can compute, we all know how to compute gradient and Hessian. I think we've seen something related in some of the talk. Yeah, the important thing is the Hessian of those things have a very good structure. And where H is a diagonal matrix, we will crucially use H is diagonal. H is just a diagonal matrix. Every entry is the second derivative of Fi. Wait. Oh, I see. My mouse is there. Okay. Yeah. A is concatenation of every row of AI. Newton method can simply be written as this. Newton method is expensive because every step you need to invert the matrix. And one difficulty is currently we still don't know how to solve generalized linear model in last step if you want polynomial time is running time. Usually if you want not too many steps, then you need to make a lot of assumptions like conditional number. But if we don't assume anything currently, the best analysis for Newton method still is square root D iteration. And if each iteration you need to solve a linear system, then you should expect the cost of solving linear programs is square root D larger than solving linear system. And this talk will show you can match them. And this is just the interval method. What happens is you have square root D or square root n step. Each step you will minimizing the function according to a different f. The interval method is like a homotopy method. You keep changing your objective to ensure convergence. But in this talk, you can think they are just the same f. And this is the interval method. It's just very look like a standard Newton method. And those ft self-concordance, a family of function approximating the origin function. Just for a picture, it's not important for understanding. Let's say f is the L1 function you are minimizing at L1 regression. Then turns out those ft will look like this. You have a family of function converging to L1. And turns out they can use that to prove something. But the trouble is you need square n step in the worst case. And what happens? Yeah, they show this algo gives epsilon accuracy after log 1 of epsilon step, square n times log. And our robust interval point is essentially the same, except I do some change of variables. So here, the origin point is this. The formula is a little bit messy, so I define this is S vector. So I define S is A transpose X such that I can just write them in a very decomposed way. So S is A transpose X. And what this new version, the number of steps is still the same. The only difference is every step, instead of computing the Hessian and gradient on your current S, every step you find some approximation of S, we call it S bar. And the crucial thing is you can think this term is a normalization. So you can kind of ignoring this. Remember, H is a diagonal matrix, so this is just some scaling of S. But the crucial thing is we are finding some S bar that is a subnorm approximation of S. And every step we find a subnorm approximation of S called S bar. We compute gradient and Hessian there, and then we use that gradient and Hessian to do our step. Here you notice this formula depends on S bar instead of S. So this is the new method. And I should say L2 version is well known. People know Newton method is robust under some L2 perturbation for when F is self-concordance. What we show is you can make it to L infinity. Notice the convergence is still not 1 for epsilon. And the approximation just need to be constant-ish. That's why you live with scaling. If some coordinate is very close to the optimal, then you leave the approximation better on those coordinates, something like that. And why this S bar is very useful. Imagine your current step, S and S bar is here, and then you do a step, you compute gradient and Hessian on your current S bar, it gives you some direction, then you move S to there. But then in next iteration, we can choose S bar there is a subnorm approximation to S. Namely, you just need to find some S bar inside this hypercube. And in general, if you want to be lazy, you want to update as little coordinate as possible. So for example, what S bar we want to choose, for example, we can choose move to there. We just update one coordinate. Then we repeat, we compute the gradient and Hessian on S bar instead of S. It gives you some direction, and then you move, and then maybe the hypercube is there, and then you move the S bar. So this is roughly what the algo will be using. And what the advantage of this robust version is, the update to S bar can be sparse. Although S bar will be still a dense vector, but each iteration will only update few coordinate of S bar. And we are crucially using just this subnorm approximation. That's why we only need to update few coordinate. And also, during the whole algo, you never really need to compute S. You just need to have some implicit representation such that you know where is the hypercube is, and roughly speaking, try to approximate the S. So we don't need to compute S exactly. And instead, what we need is we need a data structure that allows us to output S at the very last step, and also tell us which coordinate of S changed a lot. And we use that coordinate to update S bar. And you can imagine this is where randomization comes in. You can think this is a streaming problem. You have a vector, every step some coordinate change, and you want to use some sketching to detect which coordinate change and do some stuff. Yeah, any question about this? Okay. Yeah. Oh yeah. First of all, I give this talk originally in Baidu. That's why I need to make it more data science. So usually initial point is this is long. Oh, I have a pen. Or maybe I just write. Usually initial point is. Oh yeah, I cannot. Maybe do I have a pen? Okay. Good. Yeah, usually initial point is doing this. Something like this. Something like this. Usually you have a set, and then there is the initial point. But you can always collapse the dimension. I mean, you can collapse the dimension by moving the x to something like 1 infinity x log in k, something like this. Then you get a function version. That's why I giving the function version such that the formulation is exactly the classical Newton for those data science people. Yeah, but yeah, this is just initial form. Yeah. Yeah, so there's no interior in this version. They are equivalents. Yeah, usually I'm lazy on changing slides. Oh yeah, just as a warm up to see how this robust IPM is useful for ND square. Oh, by the way, you can also notice I didn't even tell you precisely what is the algo. Is very implicit in the notation. If you really want to know, you can Google survey of robust IPM, something like this, and you can see the precise formula. I'm giving a CS style of talk that doesn't give too much formula. Oh yeah, why S bar is useful? Oh yeah, classically, every step of initial point you need to invert a matrix look like that. And naively take ND square time. There is square N or square D iteration, so your one time roughly look like this. But how about the robust version? The robust version, you don't compute the Hessian on your current point, you compute on the S bar. So it's this one. And we promise you S bar is only update sparsely. Each step though only few coordinate change. And one crucial fact we are using is this rank one update of matrix. The inverse only take D square time by some explicit formula. Remember, H is the diagonal matrix. Every entries depends on some S bar I. So if one coordinate change, it corresponding to a rank one update on this matrix. So if you change one coordinate, it takes d squared time to update the inverse. And so each update on S bar take d squared time. So what is the total running time? This is d squared times the number of coordinate change of S bar. This is quite different than the classical analysis of many iterative method. Usually the classical thing is like this. We are counting how much each iteration costs and the number of iteration, and you multiply that two together is your total run time. For this algorithm, it is very different. The total run time is how many coordinate change time the cost per change. In fact, this algorithm is very special in the sense the running time is invariant under the step size. If you make the step size smaller, then turns out the update on S bar will be slower and the total running time will be still the same unless you make the step size so small that doesn't make sense. So this is, the runtime is quite invariant. So it's a good thing. And the next property is now we need to bound how many coordinate changes of S bar. And I worry there is no randomization because I'm too slow. So this is a lemma. I avoid a lot of term and normalization. But roughly speaking, in Newton method, every step the L2 norm change by 2 1 up to 1 in L2 norm. And remember, we only update the S to something that is sub-norm cost. So here is a quiz. You have a sequence of vector. Every step they change by L2 norm 1. And we just need to maintain something that's sub-norm cost. And we in total have square n iteration. Now the question is how many coordination of S bar we need to change? Anyone see the answer immediately? Turns out then you need to ask how we update S bar. The naive thing is whenever the coordinate is constant farthing, we update that coordinate. Then how many coordinate of S bar will change? Turns out this is n, if those are really the assumption, and if there is square n step. The reason is this, the number of change of S bar, because every step we change it by constant, so the number of change is bounded by the total L1 movement. And L1 movement is bounded by the number of square root of number of coordinate times L2 movement. This is Cauchy-Schwarz. And each step, the L2 movement is 1. There is square n steps, so it's square n times square n is n. And certainly, I'm hiding something. The precise version will be something like n naught, maybe n naught. Yeah, something like this is not super important. But the cool thing is this. What this is saying? This is saying for any linear programs, there is a way to update coordinates such that each coordinate only update not many times. And this is independent of condition number. Usually when we talk about coordinate descent, we still have sparse update, but the number of update or your running time will depend on the condition number. And I guess if I'm more precise, because mathematician here, there's some condition number in the law. But this is essentially each coordinate update few times. So this certainly is optimal. You need to update every coordinate at least once. So it's just log off from the optimal. Yeah, so this is pretty insane. Yeah, have you guys seen that comic? That one is a good one. And what is the total running time? We remember each coordinate update is d squared. And there is n update, so it's n d squared. This is a good running time because remember the naive way before randomization, how to solve least square form is n d squared. And we are saying linear program is also n d squared by just doing a lazy update on coordinate. And obviously after randomization, we know least square can do better than n d squared. So we study, then can we do better here? Yeah. Any question about the monster? Yeah. If for those who know, this is about procrastination. That's why I put it here. Yeah. So now we'll improve the ND square to ND-ish. Again, with a lot of offer. So now we'll focus on the case you have way more rows than the number of variables, and much larger than D. Again, this is the step. And I'm going to skip a lot of steps because we don't have time. But roughly speaking, turns out this part of the algo is very easy to maintain. Just for example, let's say I promise you only n coordinate of S change, then can we maintain AG? You can maintain in ND time because whenever you update one coordinate, you just update the vector AG. Similarly for A transpose, you can do some smart change by using some randomization. But I will skip all of those steps and tell you we can always maintain the solution in this form A transpose some vectors C, and this is a D size vector. And the trouble is we have many steps. Each step, if we multiply A transpose with this, then each step really ND times then over our budget. That's why we maintain it sparsely in this form. S is A transpose something. And at the end, what we need to find a data structure that output S at the end. This one is easy because if you already maintain in that form in last iteration, you just multiply. So this is easy. The only difficulty is tell which coordinate of S change a lot. And there is few key observation. The first observation is if you have two vectors, let's say you have two iterations, the iteration K and iteration K minus something, you want to subtract them. It's easy to subtract because you just subtract that two C vector, you get something U, then you still maintain in this implicit form. So you can subtract vector, but the problem is just detect which coordinate change a lot. Detecting which coordinate change a lot is same as you subtract two vector and tell which coordinate is large in this A transpose U. So you can think roughly speaking, what we need is just this data structure. We are given a D-dimension vector U, and we have a very tall matrix A transpose. And we want to tell which coordinate A transpose U is say larger than 1. And we want to in total find n coordinate during the whole run of robust IPM. And we allow OD time per coordinate. We have a budget of OD time per coordinate found. And turns out this is a classical problem in I think it is you can say this is a classical problem in randomized linear algebra or streaming. It is called heavy hitter problem. And turns out one way to solve this for those who already know this, then I can stop the talk here. I'm just teaching you something about heavy hitter. One way to find a large coordinate is ask for a more difficult question. Instead of finding the large coordinate, we sample a coordinate according to the entry square. And turns out for our setting, it suffices to solve this problem. And again, we have OD time budget per each sample. Then now the question is, given a vector implicit represent in this way, how can we find sample a coordinate according to some distribution, according to that vector? And turns out this is just a generic check how to do sample. Let's say we just have a vector explicitly given. We want to find a data structure to sample a coordinate according to the entries. Then what is the standard check? You create a binary tree and then do some left and right, and then some conflipping. So yeah, just to remind the task, V is A transpose U. I have 3 minutes left, and we want to sample some coordinate according to VI square. And our trick is just to binary tree. You have a tree. Every leaf here representing one coordinate of the vector. and every middle node is representing the L2 norm square of the subtree. For example, in this vertex, we want to store the information to compute sum of vi square on this subtree. If we have this data structure, then it's easy to sample. You just compute left and right, and then you just flip a coin depending on those values. And turns out we can do it by JL. This is why this is randomized linear algebra. We can the trick is this. Let's say for any subtree, what we do is we generate a random plus minus one vector only support on that subtree, and then the L2 norm V on that subtree is exactly given by R inner product with A transpose U. Remember, in this problem, U is changing every iteration, but A is still the same matrix. And how about R? R is kind of fixed random vector. So what can we do? What we can do is in the beginning of the L, you compute R transpose A. You pre-compute that. And notice this is a D size vector. Remember, the A is very tall, it has M rows, but this guy is only D size, so it is much smaller. So every step, what we do is to compute this guy, we just compute this inner product with that. This is pre-compute, so it is efficient. And you can check the total running time of those pre-computation without using any trick. Will be just ND, because all those vectors have different size support, and for most of the interval, the support size is very tiny. So you can sum them up; they are still quite small size. So our algorithm is very simple. You start the binary search from the top. You check left and right, and then you do this multiplied by U on left, this multiplied by U on right, and then you look at the value and flip a coin, and then you do a binary search. And doing this inner product, this vector by this, because this is D size, this inner product take D time. And this is binary search, there is only log n depth. So the total running time for each computation is OD. And there is log n depth, so roughly speaking, you get D log n runtime for this sampling. And this is the whole algo. Yeah, I guess the take-home story is sometimes when you do optimization, if you want to be lazy, you don't want to store your whole solution, but come up with some implicit representation and use some randomization, then you will get something. Yeah, anyway, I will stop here. Turns out you can use the same technique for many problems. You can use that to speed up STP, Meth, by part-time matching, whatever. Even for certain LP, you can solve it in linear time. Namely, each step is sublinear time cost, even though we are doing Newton method. So randomization technique is really useful. Yeah, thank you.